So what we've done in the last couple of years is work on different aspects of R. We've looked at the existing implementation. We tried to define a core semantics. Here's some Greek for those who are of that mind. That's pretty much the end, so sorry. We have defined a testing framework for R. And what I'll be talking about more today is the VM called FastR. And I thought that since not everybody is familiar with the language, I will spend a little time introducing R, explaining why it is an interesting language to have running on a JVM, and then switch to how to run it on top of the JVM. So why R? Well, R is currently the language of choice if you want to do data analysis in the small. If you're a statistician, a biologist, some users in finance, some users in other sciences. It has a huge ecosystem. There's literally hundreds of books written on R, conferences, user groups. So this is over 10 years the curve of the number of open source packages. About last year, there were over 4,000 packages of statistical routines, open source, available from the repository. By some counts, there are over 3 million R users. This picture over there is one of my favorite ones. It was on the cover of the New York Times. It's two scientists who uncovered a fraud in a cancer study, and the screen is a screen full of R code. How many times does code get on the New York Times cover? Well, R did make it. So, what makes R different from Java? Well, R is a scripting language. So R is a language for interacting with data. It's got an interpretive environment with a shell and graphics capacities. And the mode of development is slightly different than normal. So most people don't program in R. What they do is, they load a table, load some data in the image, they plot, make a plot or two, then they say, well, we'll summarize the data a little bit, then they start to make some modeling steps, then they realize, well, I'm making the steps over and over again, so they write a function, and then they're programming. But it's a very gradual slide into computing. Most R developers have exactly 1 day of training. Statistics department teach R in a day, and this is all you need to do useful things. So R is untyped, and we'll see more about it. So our goal is, to preserve all of the good things of R, to preserve the community, but move this on top of a JVM, and I'll say more about this. So a few words of history. R has actually been around for a long time. R started, the first incarnation of the language was called S. Started in 1976 at Bell Labs. It's designed by John Chambers. And then S became S+, was spawned off from Bell Labs, became a product. Then around 93, some people in the statistics community decided that they didn't really want to pay for doing statistical computing, so they started a new project called R, and R then became the de facto language that all statisticians are using. So if you're a statistician and you want to publish a paper, you are publishing the paper together with an R package that implements your results. That's completely standard. So today the R team is about 20 people, the core team. R is released under JPL, and it's in active development. So for many years, R was interpreted as an AST interpreter. About a year ago, they moved to bytecode. So they've recently moved away from 32-bit indexing. So they're moving along, but it is hard because the core team is not made of computer scientists. That's not their main activity. They're mostly statisticians and biologists. So they're doing this as a side project, and things move slow. They don't necessarily have all of the expertise needed. Okay. So if we want to summarize what R is, here's a way to think about it. R is a vector programming language. So in R, everything is a vector. Number 3 is a vector of size 1. It's a functional language, in the true sense of what functional means. I'll come back to that. It's also an object-oriented language. It's also a lazy language. It's portable, it's interactive. Another way to think about R is all of the things that it isn't, right? One of the funny things that it isn't is there is no specification. I've tried to convince the R community, let's try to specify this language. And it's amazing how much resistance there is to that, even beginning that conversation. Okay, funny. So I think they feel that if somebody tries to specify the language, it's taking it from them and turning it one of those dirty computer science thingies. So they don't trust us. But, it's been around since '93. People use it widely all over the world. So why bother? What is the problem that we're trying to solve, other than keep a bunch of computer scientists employed? Well, here's a couple of slides that will try to argue that we can do better. This is performance. There are 12 programs, they're called the language shootout benchmarks, completely unrepresentative and uninteresting programs, but they have been implemented in many languages. This is a log scale. Blue is Python, 1 is C, and red is R. Okay? So 50 for Python, 400 for R. Slow down over C code. Okay? That's not too great.
What does S8 represent?
Yeah. So there, the language shootout has about 12 programs. Look them up; they're in order. Not so S8 or so. Why doesn't Python run? I don't know. I'm not a Python guy. Complain to the Python guys. There is a paper. We have details of why it didn't run. It was appeared last year at eCoop. Here's another one, which is fun also. This is the heap allocated memory, the memory allocated by the R interpreter. Same programs. Blue is log scale. These are megabytes. Blue is C, and red. So red is the payload. Red is the actual usable data that we're thinking about. So these are the vectors that the user specified in his program, and this sort of yellowish green is the metadata, allocated by the interpreter, right? So the interpreter allocates way more data than your actual payload. Now this is, starting to give you an idea that, R may not be suited for big data. I mean, it's creating big data, right, on its own, but, without actual help from the user. So, of course, these are not at all representative programs. They're not idiomatic R tasks. They're things like building trees and stuff. So we went and looked at actual R code from the R packages and tried to understand where does the time go. So here's one package. So this is from the bioconductor. So bioconductor is this big library of biological programs, and this is one of them randomly. And we're splitting the execution time. And what this shows us is in that particular program, we're spending about 18% of time garbage collecting, then about 4% allocating concells, about 10% allocating vectors, about 8% duplicating those vectors. So R has a copy on write semantics, and these duplicates are there. Then about 5% looking up names. Then there's about, let's say 10% going to external code. So this is random libraries doing what God knows what. And then, this big red chunk is the actual R computation, operations like plus, times, and so on R data, and then some random other stuff. So that's one program. Now, if we look at a couple of hundred of them, this is what we get. And the takeaway from this is, the bottom part is GC and memory, and GC and memory can take between 30 and 40%. That's pretty high. The other thing is these light blues are external routines, and there's some programs that are dominated by external routines, but for most of them they're not. So the time is really spent in the R interpreter, and the solid red is the actual R computation. So the takeaway here is, probably we can't do much about the light blue, but everything else is something we should be able to help with. Should have a better garbage collector, and we should be able to reduce the interpretation costs. So we went on and we tried to look deeper at how people use some of the features of the language and what are the semantics. And there's no R semantics, there's just an implementation. So usually what you end up doing is, peek and poke the interpreter, see what happens. So we took a large corpus. So one of the good things about R is every program that is contributed to the repositories comes with what they call a vignette. A vignette is like a self-test. It comes with data, a little bit of code, and runs the library. So we run the vignettes, and we try to analyze both dynamically and statically what the programs are doing. And I'll give you some information from this in the following slides. And I'll mix this with a little bit of the R semantics, just to give you a feeling. So our population is this bioconductor, which is 1.4 million lines of R code. We have the shootouts, which are 900 lines, yay. And we have CRAN, that's the other big public open source repository, which has 2.3 million lines of R code, and some other stuff. So, like I said, R is a vector language. So here are bits of R code. So here I am assigning a new variable or reassigning an existing one. No type declarations needed. C creates a vector, in this case of 1, 2, 3, 4, 5 observations. And note the presence of this one, NA. So NA is the missing observation. And that is the main difference between R and MATLAB, right? MATLAB is same class of languages, but the support of missing observation is something the statisticians really felt strongly about. So every data type has an NA, and it has a clear semantics for all the operation that happens with missing observations. So here I'm adding two vectors, right? So this is done by creating a new vector and then adding it with a subset of X. Here I'm selecting the first 3 values of X and adding them to C. And the last one is kind of fun. I'm saying, well, this X that you have built over here, find all the missing observations and replace them with 0. And give me a new vector with that. Okay? So this is this is idiomatic R code. A one-liner that encompasses a bunch of loops which you would have to express over vectors in Java. Here it's just this one-liner. Okay? It does some allocation because this isNA actually allocates a vector of the same size of X, full of booleans, zeros and ones, and returns a new vector. So this is allocating actually 2 vectors. Okay? All right. So it's a functional language in several sense of the word. So just because you can have higher order functions, that's one of the meanings of functional. So yes, in R, I can create a function object. Here's a function object binding to a name. Note that I can define default argument values for arguments. So here it's any R expression, any R computation can be put in here. And that means I can call Q without a value, with a single value, or with a named value. all of three are valid calls. There's more powerful expressions I can. So this line, I don't know if everybody can see, but it is defining a function where one of the arguments depends on the value of the first argument. So it's kind of subtle how this all works out. And the 3 dot means a variable number of arguments. So one of the things we looked at was, for instance, how this fairly complex set of argument passing convention is used. So we looked at both positional, keyword, and variadic arguments, and each of these tables tells you how often they're used, and this is telling us, so this is thousands, millions, gigs of calls, and these are the number of arguments. And basically, what this tells us is, well, first, all of these argument passing conventions are used. And probably if we want to optimize for things, we need to worry about anything between 0 and 4 positional argument. We need to worry about 1 and 2 named argument, and most likely at most 1 variadic. So that's sort of the takeaway is people use these and they use them heavily in their code. And another interesting thing is there are functions with up to 20 named arguments being called. So this is this stuff is actually widely used by R programmers. Can't be easily ignored. So R, I said, is a lazy language, and by lazy, I mean I can define an assert function. So this is just a name, assert. I'm binding it to a new function that takes 2 arguments, and if the first argument evaluates to true, it calls print on the second. Well, actually, I should. I was changing my example. This one doesn't make sense. I could just. Well, I'll simplify it further. And this is what I meant to write. Tac. Voila. If C is true, it evaluates the second. And now I can call assert, and assert has the right behavior because both of the arguments are boxed into promises and only evaluated on demand. Okay? Everything is like that. Everything is boxed. So we looked at, yeah?
I've been noticing assignment statements.
Yes, there are assignment statements.
How does that interact with laziness?
Badly. I have more. Hold a bit. So one of the things we looked at is over a bunch of programs. So this gives us the number of programs, and this gives us the number of the the proportion of the lazy evaluated arguments. So the way to read this graph is that in the set of programs we were looking at, 13 programs evaluated 90% of the promises. There is about 6 programs that evaluated every single one, and no program evaluated less than 75%. So what that tells us is really most of the promises are evaluated. They're not ignored. The ones that are ignored are the promises that come with default values of arguments for functions, and these are just because they're going to be only needed if you don't pass an argument for that, a value for that argument. So how does assignment and laziness cohabit? Well, one thing that R does is that it is more eager than, say, Haskell. So in particular, if I have an assignment, the value I'm assigning into X gets forced. Same thing if I'm assigning into an array. If I have a sequencing, I have to force, and by forcing I mean evaluate the promise, make sure that it becomes a value. And the reason they do this is to give some notion of order of evaluation to their programmers. Make sense? So what that means is it's a lazy language, but it's not lazy enough to do the tricks we would like to do with a lazy language. It's like stuck in the middle. And the reason why it is designed as it is they didn't want macros, but they wanted an extensible language. And this was the one way they could think of doing it. Why didn't they want macros? I don't know. They didn't like them. Here's another funny bit. So I have two programs. Here, this one and that one, and maybe you can't see them in the back, so let me just move all of that higher up. Fine. So I have two programs. I assign 42 to C, and then I create a vector of 3 values. This program runs fine, returns a vector. And I have another program which assigns 42 to C, assigns D C to D, and then calls D. And this one fails. Why? Well, obviously, I'm trying to call the number 42. That makes no sense, right? But this one worked. Why? Because lexical scoping is context sensitive. So here, the C here, I'm looking up in the context of a function call. So the interpreter will say, find the first lexical occurrence of C. This is this one. Check that it's bound to a function. No, it isn't. Ignore it. Keep on looking.
Ouch.
It's a lazy language. How do I know it's bound to a function? Well, I have to evaluate it. So name lookup has side effects because evaluation can have side effects. They're not computer scientists, right? Don't judge them too badly. They did, hey, how many widely used statistical languages have we produced? Okay, so we looked at how many times this is used, and this feature is almost never exercised by all the programs we looked at. The only 2 cases it's exercised are for the symbol C and the symbol file. Why? Because C is the one thing you need in a R program. It creates vectors. And it's also a very handy variable once you've used A and B. Same thing for file.
Why choosing C?
Go complain. So it's also functional in the sense that it provides you with this with the property of referential transparency. So if I have y, which is some vector, millions of observations, call function f, well, any assertion that I make before the call to f will hold true after the call to f. So this gives you this notion of mathematical purity, right? Whatever f does, it doesn't change the calling environment. How does that happen behind the scene? Because I told you we have assignments, right? Well, it happens by essentially logically copying y at the call. Actually, y is not quite copied at the call. It's copied on first assignment, but logically that's the way to think about it. So the semantics says if I have a vector and I'm assigning y into it, copy y. But there's what? No. Remember, I said logically we got copied before the call. So x is always your own. You think of x as this is a unique reference to x. I have my own copy of x, so I can bang on it within a function. I can update it in place. And this is a great design choice because this is an array language. If you had to copy every time you perform an update, that would be really bad. So within a function, all of the arrays you have are your own. You can update them in place. This one, maybe not. Maybe wasn't your own. So now we're going to copy it. But it's a lexically scoped language. Actually, that wasn't the example I wanted to show you. Let me rephrase this. Yeah, I edited the slides before giving the talk, and that's a mistake. So imagine here, the x I'm trying to operate is defined in my enclosing environment. So now it's not my own anymore. So what should we do? Well, the semantics says, well, you copy this guy anyway, you create a local version of the variable x, you copy the x from above, you install it locally, you perform the side effect. That gives you, that retains the transparential, the referential transparency.
What is the bad thing that can happen with y? What if you don't copy?
What if you don't copy? What if you don't copy? Well, that's actually, I said logically, we do the copy at calls, but really they do it on assignment. It comes to the same. Yes. And lastly, they have something called a super assignment, which is, hey, I really want to modify the x that is in my parent. Do it. So 99% of .9 of side effects are local. The only cases where they go outside is when they are implementing something like a hash map. So it's mostly used well with some weirdnesses. So there's an object system. There's actually two object systems. Why not? So I didn't say this. Every data object in R, every vector, can be tagged by attributes. So every bit of data can have a hash map attached with attributes. And the way they implement the first object system is a combination of reflection and attributes. So a vector can have an attribute, and the attribute gives you the class. And it's just a string. Say, it's a man. Okay, poof. So how do we do it? I create a vector that contains only 42, and I set the class of this vector to man, and voila. And then how do I do the dispatch? Well, I have this thing called use method, which is saying, if you call this function, try to find a function named who.className. So the class name comes from x, and who is something you're passing in. And then you have functions like who.man and who.default, and it will dispatch to one of those. Okay, so you tag the data with the class, and the tag is just a string. You use reflection to find the right implementation. So we looked at how many times people redefine. So you declare a generic method, and then you provide definitions. So there's about 200 generic methods with no definition whatsoever. Most generic methods have between 1 and 2 definitions, and then it tails down all the way to 1,000. So what is 1,000? 1,000 is the print method, say. It works. And then there's another object system. So this one has classes, multiple inheritance, types, all of this, in this textual reflective syntax. It's extremely complex. So there's a team that tried to implement it for 6 months. They were trying to get the semantics right. And it's not widely used. So in the whole of bioconductor, there are about 2,000 classes and 4,000 methods. So it's like, most objects have most classes have 2 methods. And in CRAN, there's even fewer. CRAN is twice as big as bioconductor. It has 1,500 classes and only 2,000 methods. So basically, what do they do this for? To have the print method work well. Okay? But, it's there. We have to deal with it. So all of this to say, R is slow, R is a memory hog, and R has confusing semantics. So it's like this big legacy system that, the R community is having a hard time getting better performance of and maintaining. So we're coming here and we're saying, we'll do it in Java. This is sort of what they think of us, right? We're not completely sane because, first, why do we want Java? Well, we thought about it and we thought that maybe JavaScript was not fast enough. But on the other hand, hey, Java has a runtime system which we can leverage, and it's open source. Why not Java? Well, because the R community hates Java, right? You know, they've never used it. They think it's, you know, complicated. You know, they vaguely understand C, they understand Fortran, and they like R. Interaction with C will not be pleasant, and there's lots of C to be interacted with. And we have to do a complete rewrite. We can't reuse much of the existing implementation. So here's our rough approach. Sorry? There is a... Let's see. Did we consider... So the problem is, this is a dynamic language. If you don't have a JIT, you're dead, right? There's no way, you know, we will win over a C++ you know, ahead of time compiled C++ implementation. So we could implement our own JIT, we could implement our own garbage collector, but you know, it's work. You know, it's like 3 months, 6 months, you know, and all adds up to 10 years later, we're still hacking this thing. So, so what we have a grammar written in Antler. We have an interpreter that is using the truffle technology, doing self-specialization. We have implemented our own FastR runtime. Then in Hotspot, we're going to use Graal, not yet there. Currently, we're just running with the interpreter. And then, you know, we need a better, you know, ideally, we would like a better native interface than JNI, but, you know, we'll do what we can. So that's the general plan of attack. In terms of performance, what we can run today, so there's a bunch of versions of the shootout. The mean speed up is 3.3. So we're always faster than the GNU-R implementation, and, you know, sometimes up to 20, but, you know, mean 3.3. And then there's another set of benchmarks which are one-liner, mostly going down to C code, and there we're just about 1.4 times faster. So, you know, it's better, but this is without a JIT. So this is just as abstract syntax tree interpreters. Not too bad. You know, at least it gets them interested, but, you know, much more has to happen. I've been doing this since October last year or November last year. So it's, you know, it's a small team. So how does the abstract syntax tree interpreter work? Well, you know, simple things, right? We have an expression in R, this function call, and it goes to a node which will do what? Well, what this guy has to do is figure out that what is the definition of f? There's a definition of f. It has 3 arguments, a, b, c. Okay, and then it has to notice that the first argument, A, is passed last. So it will, you know, allocate a linked list, reorder them, and then call the body with the arguments in the right order. And this has to happen at runtime because we can't know in advance which F we're calling, and F can be updated, modified reflectively or what's not. So every time we do this dance of figuring out which the arguments are, and so on. So the thought is specialization will do the following, or actually this is what we implement. We put a guard that checks that we're actually binding to the same function as before, and then we do a positional call, and we rewrite in place the AST to have the arguments in the right order, and then we leave the code as is. So next time around, we only need to do the guard and a direct call. Much faster, and that's the general approach for the interpreter. Everything is done by specialization, and we specialize a lot. So how does the code look like? So this is the code of our if call, and the if call says, well, optimistically, evaluate the condition. So if has 3 nodes, a condition and true and false branch. Optimistically evaluate the condition, assuming that it's going to give you a scalar logical, a Boolean. If it does, then you can either go for true or false and evaluate true and false branches. If that fails, well, you will get an exception, and then you have catch block that will rewrite this node to a more generic node that will handle anything and perform conversion. Simple. That's the general approach. Data types. So we've specialized the data types a lot. So R has very few data types, and this is a partial list of all the data types we have in FastR, and they're all specialization of the basic types for better performance, better space efficiency. To give you an idea of the kinds of specialization we do, look at this. So I have a program that adds two vectors, stores them in a new vector, then takes that new vector, multiplies it by 2, multiply all the elements by 2, and stores that in a new vector. So we have something called views, and basically the idea is a view is a delayed operation. So this A here is pointing to a node that says, aha, you want a plus on these two vectors. These two vectors are not going to change, so I don't need to worry, and I will delay this until I need to. Then when we get here, we say, you want a view which is a times of this thing times 2. And then when we actually want to use it, we will perform all of these operations. And this is nicely parallelizable. You know, you can do whatever you want. So the views are used for larger things, and they give us this data flow representation of operation performed on things. Yes?
Do you fuse those operations?
Currently not, but obviously we could. And I'll tell you a little bit about somebody else who does fuses them. Yeah.
You mentioned that on the right side is forced on assignment.
Yes.
So with this kind of structure, you still have to force before you create it?
With this, so we only create a view if we have actually concrete values. We could, we can play games. I mean, I think in this case we would have any way to concretize them. So even if it was yeah. So inlining, simple thing in an abstract syntax tree interpreter. So here's an example. I have this function B, which is part of my shootout. It's calling A, and it turns out that if I inline the body of A, I get a 1.8 speedup. Now, this seems easy, right? Well, I see the definition of A. What can go wrong? Well, anywhere here, so everything plus square braces, round braces, everything can be redefined. So a user could define an open parent to have a different behavior. Okay? Yes?
Statically, isn't it usually obvious that they have not redefined these things?
Well, they load packages. How do I know? The square brace is a dispatch, is a method dispatch. It may have hundreds of implementation. At this point, maybe I know, but next time around, maybe somebody has loaded a new package that will dispatch it differently, or I'm getting another data type here. God knows. So the things that can change is somebody can overwrite A, or somebody can delete A, or somebody can introduce a new definition of A in my local scope. All of these are things I have to watch for. So the simple task of inlining becomes this complex, did anything in the world change? And it's not yet clear how to do it well.
So scopes are data structures?
Yes.
Yes, okay.
Scopes are data
You
structures.
can look upwards and rummage in your parent scope and
Yes.
mess things up.
Yes.
That's how I would do it.
Yes. It's the Lisp way. So Delight. So that's the last bit I want to tell you about. Delight is a project done by Stanford and Oracle. And one of the guys, TR Crump, took a couple of days and implemented Relight. So what is Relight? It's a small compiler that generates parallelized code for a subset of R. And it's written in Scala and takes the R code we have, and at runtime can generate some fast representation which can either go to CUDA or just be multi-threaded or be even distributed. So I'll give you an example how it works. It's actually quite cool, and this was just 2 days of work. So this is an sapply that goes over 50,000 elements, applying the function that sums from 1 to 10. In GNU-R, it takes 4 seconds. FastR, it takes 1.5 seconds. Both of these are pretty bad. So here's the delight version. So what the delight guys do is they just have a call delight, which takes this lazy expression, parses it, creates the equivalent delight program, and then runs in 0.4 seconds. Not too bad. We can make things a little bit more interesting by creating the sum of having multiplied this vector. So this is a vector from 1 to x, and we multiply it by 0.1 every time for 50,000 times. So in R it's 9 seconds, in FastR it's 2 seconds, and in delight it's still 0.5 seconds. Frankly, the difference between these two is kind of small, so it shouldn't go slower. And lastly, there is a more complex example. So this multiplication here was vector multiplication. We were multiplying a vector of between 1 and 50,000 elements by times.1. And that was going, slow, but not that slow. But here, almost same program where we just do a scalar multiplication. We multiply y, which is some number between 1 and 50,000, by 0 times 1s. In GNU-R, it takes 2,395 seconds. It's the same thing, right? It's simpler. This is strictly simpler than that, right? And what's going on? Well, here we're completely in the R interpreter, whereas here we were going to C code that was fast. In FastR, it takes 100 seconds. Still pretty lousy, but a bit better. And in Delight, it takes still 0.5 seconds. So this is kind of cool. And that's the kind of stuff we would like to show the R community. So to conclude, R is really a great system. It has amazing mindshare. Many people use it. So we want to keep that community around. But we need to evolve the implementation for concurrency, for better footprint, and all of that. And our proposition is, let's build it on top of a well-tested, highly performant virtual machine. And hopefully, this will become adopted. Worst thing, they can still use what we did as inspiration and keep improving their own GNU-R version. All right, that was all I had. Thanks a lot.